Hello everyone, welcome to what will be pre-lecture 26. This is before class on Friday, March 24th. So we've talked about chemical potential now, and of course the whole first half of the semester we talked about equilibrium. And interestingly enough, those two quantities can actually be tied to each other. Essentially, they're both a measurement of how likely the forward and reverse reactions are to proceed. And so for an electrochemical cell, we can relate the chemical potential, which is this E cell value, to the equilibrium constant, K here, through basically using some constants. So our dear friend R, which is the 8.314 joules per mole Kelvin, temperature being in Kelvin, N being the number of electrons transferred, and then F being a new constant called Faraday's constant, which is essentially a way for us to keep track of charge. And so this is a value given to you on your equation sheet, but Faraday's constant is 96,485 coulombs per mole of electrons. And so essentially what this does, a coulomb, in case you've never heard of that unit, is a measurement of charge. And so because we know our electrons have a negative charge, this is the charge that 1 mole of electrons has. And so that helps us balance basically, or convert between, I should say, our electrical potential and our equilibrium constant. Okay. So yeah, that is, and then things, another unit note on units is that if you were to do the units for combining all of these constants, it would work out to joules per coulomb, which is actually another way to express volts. And so in case you have not noticed, anytime we're going to be talking about potential here, we're going to be talking about it in volts. Volts is equivalent to joules per coulomb, which is what our constant works out to. Okay? All right. We actually have a way to simplify this further. Assuming that we do our electrochemical reaction at 25 degrees Celsius, which is standard conditions, then we can actually combine all of these constants except n into one. We can also undo our natural log to make it a normal log. And so this is the actual equation that you will have on your equation sheet, where our chemical potential is equal to the 0.0592 volts divided by n, which is again the number of electrons transferred in our electrochemical reaction. And that relates to our equilibrium constant K. Right? Okay, so this brings us to the Nernst equation. This is probably the single most important equation in electrochemistry. Basically continually comes up. And basically up to this point, everything we've talked about with chemical potential has been in standard conditions, meaning 1 molar of our solution, 1 atm of pressure, 25 degrees Celsius. And of course, all of the values we've looked at thus far are from a standard reduction potential table, which is under standard conditions. So what happens when we are not under standard conditions? And that is essentially what the Nernst equation does. So you'll notice that it's very similar to the equation that I talked about on the last slide that relates our chemical potential and our equilibrium value. The key difference being that, or key difference is, I should be saying, is that instead of the equilibrium constant, we have Q, which is our reaction quotient. So just a reminder, in case you don't remember, Q is the same thing as K. It's our products over our reactants, just at a non-equilibrium state. Okay, so when we're using the Nernst equation, our system has not reached equilibrium. That's of course important because if we have a battery, once a battery reaches equilibrium, it is dead. And so if we want our battery to function, we need it to be in a non-equilibrium state. And so that is why we use Q. And then we take the standard cell potential that we start with, and then we can calculate the non-standard condition cell potential. Something that I will point out in case you haven't noticed it before, when we use this little degree sign here, that means standard conditions, which is again that 1 molar, 1 atm, 25 degrees Celsius. And so if all three of those aren't met, then we are under non-standard conditions. And so we take that little degree sign off to just have the cell potential. Another thing I'll point out here is that when we're thinking about Q, I think the easiest way to remember it is Q in the Nernst equation is going to be the concentration of our oxidized thing over the concentration of our reduced thing. In just a second here, I'll show you another way that you can basically help yourself to remember that. But this is the Nernst equation. And again, I think I already basically pointed all this out. But N here is going to be the number of electrons transferred in our chemical reaction, and then we have all of our other variables listed there. Okay, so let's do an example here where I ask you predict the spontaneity of a redox reaction between iron and cobalt, with each species going between its solid form and its 2+ oxidation state. Use the Nernst equation to determine E cell when we have a concentration of cobalt 2+ of 0.15 molar and a concentration of iron 2+ of 1.94 molar. Okay, so of course this equation this question tells us use the Nernst equation. So let's start there. We have our Nernst equation, and let's fill in what we know. So we can actually calculate E standard cell by looking at our standard condition reduction potential table, finding our cobalt and our iron. And of course, one of these values is always going to be more positive than the other. So you could think of that as also being less negative, if that's helpful to you. In this case, our cobalt has a more positive value than our iron reduction potential. Also a reminder, anything you see on this table is going to be written as a reduction reaction. But we know that whatever the more negative thing is going to turn into our oxidation reaction, meaning that this reaction is going to reverse and we'll need to flip the sign. And that's essentially what we do when we subtract a negative here, it turns it into a positive. And so when we do that, we end up with an overall cell potential of 0.167 volts that we can then plug in to our Nernst equation. If we look at our electrochemical reaction, we transfer 2 electrons to cobalt, we transfer 2 to iron, so that's an easy 2 electrons that we plug in there. And then if we want to try and keep our values straight, for ox over red, one thing that I like to do to just keep it straight in my own head is I know if our more negative reaction is going to end up being our oxidation reaction. If we just think about what we learned in equilibrium, we know that we only include things that are aqueous or gas in our equilibrium expression. So if we flip this equation, like we would have to make it an oxidation, then our soluble thing ends up as a product, and our solid ends up as a reactant, so we wouldn't need to include that. Then our cobalt, our soluble thing, is a reactant, meaning that it ends up in our denominator, whereas our solid is a product, and so we wouldn't include it there. So that's just another way to keep which concentration goes where in our fraction straight. Okay, and if we plug this into our calculator, we should be able to calculate E cell, and I got a value of 0.13 volts from that. And so hopefully you did as well. And that is essentially how you use the Nernst equation. That will be it for our pre-lecture today. I hope that was helpful. If you do have any questions, please let me know. Otherwise, I will see you in class.